let's look at the core process of data preprocessing. We start with raw, messy real-world data which is never perfect. It contains missing values, wrong formats, and outliers. Our goal is to transform this into clean, organized data so our AI model can actually learn from it. This ultimately leads to better predictions and performance. In fact, data scientists spend about 70 to 80% of their time just cleaning data. To understand why this matters so much, let's look at this hospital patient admission analogy. Imagine a patient arrives at the hospital in an emergency with missing or confusing info, like forgetting their blood type or having an age written as a word instead of a number. Before any surgery can happen, the team must collect and clean all this information. Only then the surgeon, which represents our AI model, can do their job effectively to ensure a successful outcome. The first major issue we face in raw data is missing values. This happens when we have empty cells because someone forgot to fill them in or the data simply wasn't captured. Looking at our customer data table here, notice that for customer 1002, their age is missing, marked as NAN or not a number. And for customer 1003, their income is also NAN. We have three main strategies to handle this. First, we can simply delete the row. We only do this if very few rows are missing, usually less than 5%. You can see the row for 1002 is completely removed in the result. Second, for numerical columns, we can fill with the mean or median. For example, we replace the missing age with 31.5, which is the average age of the other customers in the dataset. Third, for categorical columns, we fill with the mode. If a city was missing, we'd fill it with the most common category appearing in the data, like Mumbai. By carefully applying these strategies, we ensure our model learns from a complete, well-structured dataset. Next, we'll look at another issue that can drastically confuse our model: extremely high or low outliers. Now, let's dive into the specific problems we face when cleaning data. The second major problem is dealing with outliers. An outlier is a value so extreme that it is probably a mistake, and leaving it in will completely confuse the AI model. For instance, look at this single dot standing far away from the rest of the data points. If we examine this list of employee salaries, most of the values are reasonably clustered around 35,000 to 42,000. But then we have this value of 9.5 million. As noted here, this is clearly a typo or a data entry error. To fix this, we use statistical tools like box plots to automatically spot them. Once detected, we can either cap the value to a reasonable upper limit or simply remove the record entirely. Moving on, the third problem is having wrong data types. This happens when numbers or dates aren't stored in a format the computer can mathematically process. Take a look at this age column. You see the values 28, 35, and 42, but notice that these numbers have quotes around them. That means the system is reading them as text strings, not actual numbers. Is the same story if we look at the date column below. We have three completely different formats representing dates. AI can't process that chaos. To resolve this, we use programming functions to force all of these into a clean, uniform format before feeding it to the model. The fourth data preprocessing problem involves categorical encoding. Here is the core issue. AI models are mathematical engines. They only understand numbers. They cannot process text labels like Mumbai or mail. We absolutely must translate words into numbers. There are two primary ways to do this. The first is label encoding, which is great for categories that have a natural order or simple binaries. For example, we can assign male as 0 and female as 1. But what if the categories don't have a ranking, like different cities? That's where we use one-hot encoding. Let's look at this before and after example. Instead of assigning a single number to each city, we create a new column for every possible category. If a person is from Mumbai, we look at the newly created Mumbai column and put a 1 there. Because they are in Mumbai, they can't be in Delhi or Pune. So those columns get a 0. Similarly, for Delhi, the 1 goes in the Delhi column and the rest get zeros. The ultimate goal of all these steps is to transform messy, human-readable data into a pristine numerical format that algorithms can ingest. But even after converting everything to numbers, we still face a massive hurdle when those numbers operate on completely different scales. Now, after handling those extreme values, we hit the fifth and arguably most critical problem for AI, feature scaling. This happens when your different columns have wildly different ranges of numbers. Take a look at this dataset here. We can compare the age column, which ranges from 18 to 65, to the salary column, which ranges from 25,000 to 5 lakhs. Because the salary numbers are so much larger, an AI model will mistakenly think salary is 10,000 times more important than age just because the raw numbers are bigger. We need to bring everything to a similar scale so the model treats them fairly. One way to fix this scaling issue is min-max scaling, also known as normalization. This technique simply squeezes all your values into a tight range, specifically between 0 and 1. Here is how it works. We take our original value, subtract the minimum value in that column, and divide by the total range, which is the maximum minus the minimum. By doing this, we find exactly where the value sits as a percentage of the whole. For example, if the age range is 18 to 65, and age of 35 is calculated as 35 minus 18 divided by 65 minus 18, that equals 0.36, which means 35 is 36% of the way through our age range. Another very common method is standard scaling or standardization. Instead of trapping values between 0 and 1, this transforms the data so that the average of all the numbers becomes exactly 0. And the standard deviation, which measures how spread out the numbers are, becomes 1. Let's apply this to our age example. If the mean age is 40 and the standard deviation is 12, an age of 35 results in 35 minus 40 divided by 12. This equals negative 0.42. That negative sign is incredibly useful. It instantly tells us this person is below average in age compared to the rest of the group. Knowing when to use which method is vital for your model success. As a general rule of thumb, you want to use min-max normalization when you know your data is between fixed bounds or when working with neural networks and image data. On the other hand, you should use standard scaling if your data has outliers or if you are using most common machine learning algorithms like SVM or KNN. Now that we have covered how to clean and scale our data properly, we can build a complete, reliable data pipeline. Let's step forward and visualize how raw, messy data travels through all these steps to become completely model-ready. To visualize the whole journey we've been discussing, let's look at this raw data pipeline. We start with garbage in over here, messy data with missing values and wild outliers. We pass that raw data through these specific pre-processing steps, filling missing values, encoding text, capping outliers, and scaling. The final result is gold out, clean numerical data that is completely model-ready. A fantastic real-world example of this is seen at Meesho, an e-commerce platform. They receive raw data from 50,000 sellers. Before their AI can forecast demand, they must run through these exact steps, filling blank product weights, capping price typos, encoding categories, and scaling prices. If they skip these steps, their predictions are total nonsense. But after pre-processing, their accuracy improved by 34%. HDFC Bank provides another powerful example. For their credit scoring model, they require a strict 4-step pipeline. First, they handle missing data by filling employment durations with medians. Second, they manage outliers by capping extreme entry errors at the 99th percentile. Third, they use encoding to turn loan purposes into binary columns. And fourth, they apply scaling
to bring income and credit scores into the same manageable range. By doing just this, a simple model's accuracy jumped from 61% to 84% without changing the AI model itself. Now, let's walk through how this looks in code using an HR dataset. Here is our raw, messy data. In step 2, we standardize the gender column by stripping spaces and capitalizing the text. In step 3, we handle outliers in the salary column using the interquartile range, clipping values outside the normal range. Step 4 imputes missing age values with the median. Steps 5 and 6 tackle encoding. We label encode binary gender and use one-hot encoding for the department. Then we scale the numeric columns, resulting in this nice scale data. You can see the effect clearly in these box plots, showing how scaling shrinks the data into a usable uniform range. To test your understanding, consider these common scenarios. If a car dataset has 15% missing mileage, deleting rows means you lose way too much info. You should impute it instead. When encoding, remember that label encoding creates a hierarchy, while one-hot encoding avoids this issue. And scaling matters because AI models use distance to calculate relationships. Unscaled massive numbers will completely drown out smaller ones. For practice, you can try cleaning this ONGC dataset by applying these exact same methodologies. The ultimate takeaway is simple. Garbage in equals garbage out. But if you build a robust pre-processing pipeline, you get gold out. Clean data doesn't just make your spreadsheets look nicer, it leads directly to better models and higher accuracy. You are now equipped to transform messy, real-world data into high-quality fuel for any machine learning model.